So on Wednesday, we kind of started to talk a little bit about nephrons, right? Or did I just completely tell you guys what we talk about today? I can't remember exactly what we got to in this class. On Monday, sorry. Did we get to talk anything about nephrons whatsoever? Or did I just say, are we going to wait? I thought so. Okay. So, within our kidneys are these little structural units called nephrons, and there are millions of them, over 1 million per kidney, and structurally they consist of two parts. The renal corpuscle, which is what's pictured here on this page, and then a long winding tube called a renal tubule, okay, which is obviously not pictured on this page. Okay, this is a picture of a singular nephron. Okay, nephrons are contained to two parts of a kidney. The two major parts of a kidney are the renal cortex, which is this lighter shaded outer part of the kidney, and the middle, which is the renal medulla. Okay, this darker shaded brown region. If you've taken anatomy, you've learned this before. If you're taking anatomy, you're going to learn this afternoon, okay? So that's kind of nice for both ends. It will be either covered today or previously covered, okay? Unless you haven't taken anatomy yet, and in that case, you'll learn it later. So, the first part is where we first begin the making of urine, and that's called the renal corpuscle. Okay, there are three major parts to the renal corpuscle. And basically, I'm going to go back a couple slides to talk about it, because that's right here in a better zoomed-in view. Okay, we have what's called an afferent arteriole, a glomerulus, and then an efferent arteriole. Okay, so we've got blood coming in to our first part of our nephron. Okay, blood comes in by way of the afferent arteriole, which you can see here with our red arrow. Okay, this immediately branches into a mass of capillaries, which you can't really see the capillaries because they are covered with some special cells called podocytes. Okay, the cells are called the capillaries are called a glomerulus or glomerular capillaries. Okay, it's a network of blood capillaries. Okay. What we do is we actually suck most of the water out of the blood right here. That blood is sucked almost dry, and the water will collect into this, what's called the capsular space. Okay. Surrounding the entire structure is a capsule, which is not really important physiologically. But this stuff that collects here, which is going to be water and small things like solutes, ions, salt, glucose, urea, they're going to collect and form into what's called glomerular filtrate. Okay? Or as it's written here, sometimes just filtrate. Okay? We then collect that filtrate and run it into the first part of our renal tubule, which you can see here is labeled as the proximal convoluted tubule. In order to get out, the stuff has to pass between the finger-like extensions of those podocytes. Okay. If you think of those podocytes and their little foot-like or finger-like extensions, like what I'm doing with my fingers right now. Okay. I'm locking my fingers in, but in a way that you can still see little gaps between my fingers. Okay. Those gaps are not fluid type. If I were to go over to the sink and try to collect water into my hands, it'd be very difficult because the water is going to leak through, right? Okay. If I were to take something else into my hands that's really large, I might be able to hold it because those large objects might not be able to fit through those little crevices. Okay. Things like red blood cells, white blood cells, platelets, plasma proteins will not fit in these tiny little gaps. Small things like water and ions will. Okay. So that's what we do here. Okay. Then we run it through this long tube, okay, which I'm going to come over here to talk about. we've got 3 1/4 major sections to this renal tubule. We have what's called the proximal convoluted tubule, a loop of Finlay, which is also known as a nephron loop. Okay, nephron loop is kind of the new term. Loop of Finlay is kind of the old term. Okay, I learned it as a loop of Finlay. That's what the older versions of the textbook knew it as or talked about it as. I think this was the very first time that they switched gears and used nephron loop instead. Okay, it might not be a bad idea to somewhere put in parentheses nephron loop or loop of Finlay mean the same thing. Okay. The key with the nephron loop or loop of Finlay is it dips down into the renal medulla. Okay. You've got then the filtrate flowing this direction back up into the cortex by way of a distal convoluted tubule. Do you guys know what the word convoluted means? It means jumbled up. Okay. You can hopefully see why we call it a convoluted tubule. Okay, both proximal and distal. Okay. Now, the distal convoluted tubule and this tube, which is called a collecting duct, are where we finalize the urine formation. Okay, there are cells here that are sensitive to things like aldosterone and antidiuretic hormone. Okay. Do you guys remember the nickname for aldosterone? It's our salt retaining hormone. We're going to pull more salt out when we secrete that hormone, which means we're going to pee less salt out. Do you guys remember what antidiuretic hormone does? It makes you pee out less water. Okay? So what we will do here is suck salt and water out of these two parts and put it into the bloodstream. We call that reabsorption. Okay? Notice how there's a lot of blood vessels that surround our tubule. Okay? That's where the stuff can re-enter the blood. Okay? We said we sucked the blood dry up in our corpuscle, but we pulled most of that water right back into the bloodstream right here, actually. Okay? Those peritubular capillaries are the routes at which we get the blood back, or get the water back into the blood, and the ions, the salt, whatever. Okay. Now, this is kind of a complex look at various things anatomically. Okay. We are going to talk about the process that takes place here, what we call filtration. Okay. We'll talk about reabsorption, which is where we pull stuff out of the tubule. And we're going to talk about secretion, which is where we take stuff from the blood in these parts and put it into the tubule. Those are the 3 processes in which we make urine. Those are actually shown on the next page. Okay. Before we move on, I want to talk a little bit more about these anatomical structures. The proximal convoluted tubule is going to be made up of cells that have microvilli. Remember, microvilli are those finger-like extensions that increase surface area. Okay. We reabsorb most of the water right here, and the cells that line that tube there are going to allow for easy passage of that water into the cells. Okay. Then they can enter the bloodstream and become part of our body. Okay. The loop of Henle is not going to contain cells that are having microvilli. Instead, they're going to be of different shapes. Some are going to be simple squamous, some are cuboidal, some are columnar. Okay, that's not super important. But we've got 2 parts, a descending limb and an ascending limb. Okay, because that's the flow that occurs. It drops down the descending limb and then goes back up the ascending limb. Okay. Something special happens in these 2 limbs. Okay, we'll talk about this on Monday, but we pump out salt on this side, and we do so in the parts that are really thick, which you can't really see. The parts that are really thin, which you can see over here on the left side, are permeable to water, whereas these are not so much permeable to water. Do you guys remember what the word permeable meant? Let stuff go through. So water can escape out of the tubule here. And that's going to continue the same thing, or the same way as it did here. The reason water gets pulled out here is because it's chasing after the salt that's pumped out over here. They say that if you were to lick or taste the middle of a kidney, this part in here is going to taste really salty. Okay, because of the salt that collects in this area. And as we learned earlier in the semester, water goes where things are salty, or where there's lots of solutes, like salt. Okay. The last thing I want to talk about before we move on is this little part right here that I'm circling with my mouse. Okay. Notice how our afferent arteriole, that blood vessel that brought blood into our nephron for the first time, is being brushed by the distal convoluted tubule. Okay. That segment right there, it might not be a bad idea to label, is called the juxtaglomerular apparatus. Okay. This word, juxtaglomerular and then apparatus, is located right here. Anybody know what the word juxtapose means? It means next to. So the word juxtaglomerular literally means next to the glomerulus. Well, there's the glomerulus. Hopefully you see why we call it that. Okay. There's an analogy I'm going to use in a little bit. I call it the Barbie doll or G.I. Joe analogy. It doesn't matter what we're talking about. It's a conveyor belt, assembly line analogy, more than anything. There are cells that line that tubule. Okay, here I went back a couple slides to show. Here's the juxtaglomerular apparatus. Okay, this is our tubule in yellow next to our afferent arteriole. Notice how closely associated they are with one another. These cells are called macula densa cells. They monitor the stuff inside of the tubule. And if we are making urine too fast, they can basically kink off this blood vessel, which is going to slow everything down from the beginning. Okay. And so I'll talk about that process here in just a little bit. So those are the anatomical features of a nephron. And they are what allow us to perform the three processes of urine formation. Okay, we've already talked a great deal about filtration, and I'm going to continue talking more about it today. Okay, that's the first step. But don't you guys like this image a lot better than the one I was on the previous page? It's a lot simpler, okay, but it's not nearly as, obviously, helpful, okay, as seeing the real thing. The first step is where, in green arrow, we're showing it really nicely. We're bringing blood in to the capsule and then sucking it dry. Not necessarily completely dry, but we're pulling out a lot of its water. Okay. Now, what's left in the blood will exit as the efferent arteriole and will then branch into those crazy capillaries called peritubular capillaries. Okay. The importance of that is because that provides us a route to pull stuff back into the blood. Okay? We're not going to continually pee every second of every day like we would if we didn't pull that water right back in. You'll see a number of how much filtrate we form each day and how that's nowhere near the amount of urine that we pee out every day. Okay? We are going to perform reabsorption, and this primarily takes place in the proximal convoluted tubule, but it also occurs in the rest of our tubule. Okay, this is the return of the stuff back to the blood. Notice how it's called reabsorption and not absorption. We used the word absorption back when we talked about the small intestine and the rest of the digestive tract. Okay, remember when we take a drink of water, that water is in our stomach and then in our intestines, technically not a part of our body until it's brought through the wall of those structures and enters our bloodstream. That first time that stuff enters our bloodstream is called absorption. The return of it back to the blood is why we call it reabsorption. You throw prefix re at the beginning of a word, it means doing it again, right? Okay. Now the opposite of reabsorption is secretion. Okay. Secretion is where we take stuff from the blood and put it into the tubule. Okay, and that will eventually become urine that's then peed out. Okay, it gets filtered down into our bladder and then gets peed out through our urethra. And we'll talk more about that next week. Okay. Now, it says here in the figure 1, 2, and 3, but you have to know that steps 2 and 3 are not chronologically ordered. Doesn't necessarily mean that we do reabsorbing and then secreting. Those processes are kind of happening together at the same time. Does that make sense? So at some points we're pulling stuff into the blood. Other points, or at the same time even, we might be pushing something else out of the blood. Okay. So if you want to actually calculate urinary excretion, so getting rid of urine, it would be the amount of filtrate plus secretion minus reabsorption. Okay. Notice how the tubule is colored yellow, as is the arrow from the blood into the tubule. Why do you think they color it yellow? What color is urine? Yellowish, right? Okay. Which I love that they do that, because it makes it so easy to kind of follow. Okay. This process, or these three processes, will help nephrons maintain homeostasis by way of controlling blood volume and composition. Remember, volume is the amount, composition is what's in it. Obviously, we're going to go into greater detail with all three of these, and that begins with filtration. Once again, takes place within our capsule and what's called the renal corpuscle. Okay. So the blood comes in, and then it branches throughout this network of capillaries. And in order for that stuff to leave the blood, it has to cross through these three layers, which are called the filtration membrane. It's kind of like the respiratory membrane existed in our lungs, which is what oxygen and carbon dioxide had to cross. This is a little more complex for good reason. We don't want everything leaving the blood. We just want the small stuff. Water, vitamins, glucose, amino acids, small plasma proteins, ammonia, urea, and ions. Nowhere in there are red blood cells, white blood cells, or platelets. Especially those should never be in urine. Okay, so the first layer that they must cross is through the actual capillary wall. The great thing about the capillaries here, those glomerular capillaries are fenestrated, which means they've got all these tiny little holes. Okay. Basically, they are super leaky pipes. Not super leaky as in they have huge holes, they just got a whole bunch of small ones. Okay. Which makes them permeable to many substances, but not permeable to red blood cells, white blood cells, or platelets. Okay. Red blood cells cannot fit through those little holes, hopefully. Neither can proteins that are good sized. Okay. The second layer surrounding that is called the basal lamina, which is an acellular material made up of collagen. That says collage, but there should be an N there, sorry. And proteoglycans. This matrix is negatively charged, which actually prevents anything that's negatively charged from wanting to go there. You guys remember how we talked about opposites attract? Positives and negatives like each other, right? Well, two negatives hate each other. Like charges repel. Okay. So anything that's negatively charged here is not going to want to go there. They're also not going to want to go to the third layer, which is the little gaps between the finger-like or foot-like podocytes. Okay. My fingers, how I'm showing you, have those gaps. The gaps are called filtration slits. Okay. Okay. And they carry a negative charge, providing another obstacle for large molecules. Spanning across that is a slit membrane. Okay, it is basically another drain or strainer. Okay, that only allows things this tiny, 0.006 to 0.007 microns. That's basically nothing. I mean, that's so small. That's almost, almost nothing. Okay. Things like water, glucose, amino acids, yada, 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 they can fit through there, though. Okay. Red blood cells, proteins, platelets, that stuff is not. Okay, and that's good. We don't want that stuff in our urine. Okay, so our principle of filtration is based on pressure. Pressure gradients have to be established that drive the water and solutes out of the blood and into that capsular space. Okay. The same thing existed with regards to other capillaries. Okay. We've seen this before, so it's nothing new. Okay. A big difference is we're pulling more out of our renal corpuscle from our blood than our other capillaries. Why? Because of these three things. The capillaries here have a large surface area, which provides for a lot of ability to pull stuff out. Okay. The filtration membrane, like I said, is really leaky. 50 times leakier than most of our capillaries. The other capillaries that we talked about this semester are called sinusoids, which were found in like your spleen and bone marrow, were huge holes. They had those huge holes that allowed blood cells to pass through. That's not what we're talking about here. Okay, these were the ones in the middle. Okay. The blood pressure within the capillaries is really high. Okay. That creates a pressure gradient to push the fluid out. Okay. And that's because of the difference in the size of the afferent arteriole and the efferent arteriole. Okay. The afferent arteriole is what brings blood into the corpuscle. The efferent arteriole is what drains it. The efferent, that is skinnier in width than the afferent, which means that we can bring more in than we can drain. So it's not equal coming out as what was coming in. So the pressure in here builds up. Okay. That pressure in these blood vessels is called glomerular blood hydrostatic pressure. This pressure is pushing out and therefore promotes filtration. There's also two pressures that oppose filtration, and that's why the arrows are pointing in. We have capsular hydrostatic pressure, which is the pressure inside of the capsule, and then pressure within the blood from the stuff dissolved in it. That helps try to prevent stuff from leaving. Okay. So in order for filtration to occur, we have to perform a calculation to determine if it's going to actually occur. I should state that better. To determine if filtration is going to occur, we have to do a calculation. That calculation is called NFP, net filtration pressure, which is the total pressure that promotes filtration, and it is the pressure that promotes, dBHP, minus the two that oppose. Now, you aren't going to need to know anything calculation-wise other than if it's positive, filtration occurs. If it's negative, no filtration occurs. We actually learned this a couple weeks ago. This was stuff that we talked about back when we talked about blood vessels. Okay. So hopefully you guys can kind of remember that. Now, those pressures and the resulting NFP are directly correlated to the rate at which we form filtrate. which is described as GFR, glomerular filtration rate, which is defined as the amount of filtrate that we form in all of our corpuscles of our kidneys each minute. It's 105 mils a minute. That's in females and 125 in men. If you calculate that up for an entire day, that's 180 liters or 45 gallons of filtrate a day. Do we pee out anywhere close to that? Good. Okay. That would mean we basically never stop peeing. So, we would never be able to stop drinking. What we do, though, is we do filter it out, but as I've been saying, we put it right back into the blood. So, most of the glomerular filtrate must be returned to the blood and recycled. Homeostasis of body fluids requires our kidneys maintain a relatively constant GFR. So these numbers, 105 mils per minute, 125 mils per minute in men, they should stay the same, pretty much constant. Okay. If it's too high, we might lose too much. Okay. It means we're producing too much filtrate and we can't return enough. Therefore, we might lose stuff in our urine, stuff that would not be needed to be lost. If it's too low, we might not be able to get rid of the waste that we need. We talked about the other day how bad it is if we have too much waste in our body. Okay. As I mentioned, GFR is directly related to NFP. So any change in NFP causes changes in GFR. So by changing NFP, we can also change GFR, which is going to be how we can regulate GFR, and that is the three things that you have to write down at the bottom. We have what's called renal autoregulation. What does autoregulation mean? We know what auto means. It's self. So this is how the kidneys can self-regulate. Neural regulation refers to the autonomic nervous system. We're going to talk sympathetic today. What do you think sympathetic nervous system activity does to our filtration rate? What does sympathetic activity cause? What's that response? Fight or flight. Okay? So, let's think of it this way. When we are running away from a bear, do you think we want to form more or less filtrate? I've got to vote for both. Think of it this way. When we're running away from a bear, are we at all concerned with making urine?
I probably pee myself.
You might pee yourself, but you've already made that urine. Okay? You're not making more. Two reasons why. Obviously, we're not worried about that, but more importantly, we want to conserve the water that we have because we're sweating and losing water as a result of running. And two, we are going to basically shut down blood flow altogether to the kidneys so that we can distribute it to the things that need it, our skeletal and cardiac muscle. We'll talk more about this in a little bit. And then we're going to talk about hormones, how they regulate GFR.
On the Engage app.
I already did.
I
You did?
messaged her
My head is going to
on
explode.
Facebook, but she not even opened it, so.
Okay, so like I said, autoregulation refers to the ability of our kidneys to regulate themselves. And it's actually down into the nephrons themselves, which allows them to adjust their own blood flow without any external control. And so we're talking nervous or hormonal changes, which allows them to maintain a stable GFR even if arterial blood pressure outside of the kidneys is completely changed. Two mechanisms exist with regards to autoregulation. The first is the myogenic mechanism. Do you guys remember what the prefix myo meant? Muscle. Good. This involves the smooth muscle that lines the afferent arteriole. The afferent arteriole, remember, was the one that was bringing blood into the corpuscle. Okay? When we have an increase in blood pressure, it's primarily due to a surge of blood. So there's extra blood in the blood vessel. So what do you think that does to the stretch of the afferent arteriole? It increases the stretch. The cells that line those blood vessels are going to detect that stretch. And if we have a surge of blood flow, what do you think happens to GFR? It's going to increase, right? We've got more blood, we can filter more blood. Well, we're going to perform negative feedback to bring that back to normal. So we can respond to that surge of blood flow by basically vasoconstricting and kinking this up a little bit. That's going to be what happens when GFR increases as a result of arterial blood increases, blood pressure increases. The opposite is going to occur when arterial blood pressure is low. Okay, and those muscle cells are stretched less, allows them to relax, afferent arterioles dilate, and increase GFR. This is an important mechanism for very quick response to maintain GFR shortly after changes in blood pressure. Okay. I have a feedback loop here on this page. It's kind of different than the ones in this textbook because it's from a different textbook. Okay. So we have normal GFR, something causes increases in arterial blood pressure. We don't care what the change is causing, or we don't care what is causing the change, we just know it's increased arterial pressure, which causes increase in GFR. At that same point, the stretch of the afferent arterioles goes up, and we're going to release calcium in order to cause muscle contraction to increase resistance. So we're vasoconstricting. Vasoconstriction means less blood flow in the arteriole, which decreases GFR, and that's how we restore normal GFR. This is what type of feedback? We're opposing the change, it's negative. Okay. Tubuloglomerular feedback involves that juxtaglomerular apparatus. That section of our distal convoluted tubule that brushed past that afferent arteriole. This is my example that I was talking about with the Barbie dolls on an assembly line. Okay, so let's pretend that we are all making Barbie dolls or G.I. Joes on an assembly line. Okay, one of us is at the front, and our job there, whoever's sitting there, is to pop the head on the doll. Okay, pop the head on the torso. Next person pops an arm on. Then the next person pops another arm. Then a leg, then the clothes, and then the person at the end puts it in the package and seals it up. Okay. What happens if the conveyor belt speeds up to a point where somebody down the line can't keep up? Barbie dolls are not going to get put together correctly, are they? So what happens in that situation, hopefully for that individual, is they have a little switch they can hit to say, hey, let's get this thing slowed down a little bit. Okay. They can slow the conveyor belt down, therefore they can catch back up. Our nephrons have essentially this capability. If I go back to my picture of a nephron, I can hopefully really show it. Okay. The cells here in the tube detect two things: the concentration and the amount of filtrate. Okay. If we are speeding up things to the point where we're producing too much filtrate, we might end up peeing out too much water or too much salt or whatever. Okay. And so to slow things down, we can cause this blood vessel, where it all began, to decrease its flow. So we shut down blood flow into the glomerulus, therefore decreasing GFR. Therefore, we are able to slow things down altogether and not lose vital things. Okay. The opposite occurs when blood pressure drops and GFR is lower than normal, but this is slower to, this is to a lesser degree. This feedback is longer term and slower than that myogenic mechanism, which should make sense because it takes a long time for that filtrate to make its point to the distal convoluted tubule and things to really progress from there. Okay. This feedback loop is illustrating that process. And it is negative feedback that this operates by as well. Any questions on autoregulation? Okay, let's move on to neural regulation. We've already did a pretty good job of figuring this one out. Control of GFR neurally is by activation or lack thereof of the sympathetic nervous system, which, if it's active, will release norepinephrine. Norepinephrine causes vasoconstriction of arterioles in the kidneys, especially those afferent arterioles. At rest, is the sympathetic nervous system active? No, right? Because we're in rest and digest mode, right? Parasympathetic is active. So at rest, there's moderately low, or basically no sympathetic. So both the afferent and the efferent arterioles are dilated, and therefore there's no real effect from the nervous system. Instead, autoregulation is what's controlling it. GFR, that is. Okay. If we activate the sympathetic nervous system moderately, both the afferent and efferent arterioles will constrict to the same degree, causing a slight decrease in GFR. And if that bear pops out of the woods and we have great sympathetic stimulation, and we have to exercise, or if we have a blood hemorrhage, we're going to constrict the afferent arterioles more than the efferent, meaning that there's less blood flow coming into the nephron altogether. As a result, GFR drops significantly, which allows for reduced urine output, helping to conserve our blood volume. We don't lose as much water. That's great, especially when we're exercising, okay, for a variety of reasons. And we then can distribute that blood to the tissues that need it. Who needs the blood when we are running away from a bear? Our skeletal muscle and our cardiac muscle. And this is stuff that we've talked about throughout the semester. The final way that we regulate GFR is by hormonal means. Two major hormones are involved in this process. Angiotensin II, which is part of that wonderful angiotensin-aldosterone mechanism, renin-angiotensin-aldosterone mechanism. And then an atrionatriuretic peptide, which we talked about back in Unit 6. We also talked about this mechanism as well back in Unit 6. Atrionatriuretic peptide is a hormone actually produced by our heart's atria. They're stimulating the release of this hormone in response to basically too much blood. And a great way to decrease blood volume is by getting rid of the water in the blood. So when we release atrionatriuretic peptide, we're going to promote the increase of GFR, which means that we're more likely to pee out water. Okay. The renin-angiotensin-aldosterone mechanism is a little more complicated, And its stimulus is a decrease, of blood pressure. So we're going to do a whole bunch of different things that promote increased blood pressure. Okay? So, begins when blood pressure drops and our sympathetic nervous system signals cells in the juxtaglomerular apparatus to secrete the enzyme renin. The renin hormone, or enzyme, is released by the kidneys themselves. It then causes a series of events that cause us to convert angiotensin II from angiotensin I. Angiotensin II is the hormone that does all these different things. It causes widespread vasoconstriction. Well, we learned earlier if you vasoconstrict, what happens to blood pressure? Goes up. Okay? There's one thing that we can do to increase blood pressure. We're going to constrict both the afferent and efferent arterioles to reduce GFR and water loss. So we're going to pee out less water, so less water will go into our urine. Any loss of water in our urine is going to affect blood volume. So if we decrease water in urine, we increase our blood volume. And any increase in blood volume causes increases in blood pressure. Okay. We stimulate sodium chloride and water reabsorption. So we're peeing out less salt and less water, which increases blood volume. We stimulate the adrenal cortex to secrete aldosterone, our salt-retaining hormone. Causes increases in blood volume. Secretion of antidiuretic hormone is going to occur. Antidiuretic hormone means we pee out less water, which increases blood volume, therefore increasing blood pressure. And finally, we will start to become thirsty, which is going to be what causes us to ultimately grab a glass of water and take a drink, increasing blood volume, therefore increasing blood pressure. So it's a very complicated way, or multiple ways, that we ultimately increase blood pressure. I know this figure looks super complicated, and it probably is to a certain degree. This is explaining all those mechanisms of that renin, angiotensin, aldosterone mechanism. And if you really wanted to, you can kind of walk yourself through that. Okay. Or you can kind of just refer to table 26.2, which is the table that summarizes all those various mechanisms of GFR regulation. We have the two autoregulation means, neural, the two hormonals. Notice that decrease for everything except for atrionatriuretic peptide. Now, remember, there's 3 steps in the formation of urine. That was just step 1. The great thing, in my opinion, is I feel like step 1 is kind of the most complicated. Okay. We still have tubular reabsorption and tubular secretion. Okay. So we're running out of time, but we can do 1 or 2 more slides. Well, we can still have the ability to think. So, tubular reabsorption, remember, refers to the return of substances from the tube into the blood. Like I said, 99% of that water that we just filtered out is going to return back to our various structures. Primarily, we're talking about the proximal convoluted tubule. The PCT as it's abbreviated here. Okay. Now, the cells of our proximal convoluted tubule are going to have microvilli, which allow them to reabsorb with great quantity. Okay. But we don't always absorb the stuff directly into the cell. Sometimes it passes between the cells. That's called paracellular reabsorption versus transcellular, which is where they actually pass through. And that can be illustrated with this image on this page, a couple slides from that one we were just on. The only difference is the direction of travel. And not direction as in, let me not use the word direction of travel, but if it travels through a cell or not. Para, it travels between cells. Trans, remember that prefix always means across, through. So this is where the cell actually absorbs the substance, I should say reabsorbs the substance, and then it goes into the bloodstream, whereas in para it goes between the cells. That's it. That's the only difference. Ultimately, the same result is moving it into the bloodstream. Is there anything to write on this page? Okay, go ahead and write that down, and then we'll pick up with this on Monday. Okay, have a fantastic weekend.